Tonight, we travel into one of the deepest mysteries in modern science. An invisible force, quietly stretching the universe itself. Galaxies drift farther apart. Space slowly expands in every direction. And somewhere within that vast darkness, scientists discovered something unexpected. The expansion of the cosmos is accelerating. No one fully knows why. The force behind it was given a simple name: dark energy. So, wherever you are listening from tonight, settle in gently, and let us begin with the story of how humanity first realized the universe was not standing still. For most of human history, the night sky appeared calm and unchanging. The stars moved across the heavens in familiar patterns. Seasons came and went. Constellations returned year after year. To the people standing beneath it, the universe felt stable. Ancient civilizations watched the sky carefully. They tracked the motion of planets. They predicted eclipses. They built temples and calendars around celestial cycles. But even as astronomy became more precise, the larger universe still seemed motionless. A vast and silent backdrop. In the early 20th century, many scientists still believed the universe itself was static, not expanding, not shrinking, simply existing. Even Albert Einstein originally believed this. When Einstein developed the theory of general relativity in 1915, his equations described gravity as the bending of space and time. Massive objects distort the geometry around them. Planets follow curves through that distorted space. The theory was elegant. It explained motion with extraordinary accuracy. But there was a problem. Einstein's equations suggested that the universe could not remain perfectly still forever. Gravity pulls matter together. Galaxies attract one another. A static universe would eventually collapse inward under its own gravity. Einstein found this unsettling. Like many scientists of his time, he assumed the universe was eternal and unchanging on large scales. So he adjusted his equations. He introduced something called the cosmological constant, a small mathematical term, a kind of outward pressure, something that could counteract gravity and keep the universe balanced. For a while, the idea seemed reasonable. But far away, new observations were beginning to change humanity's understanding of the cosmos forever. In the 1920s, astronomers started building more powerful telescopes. Among them was an American astronomer named Edwin Hubble. Hubble studied faint patches of light in the sky called nebulae. At the time, scientists debated what these objects really were. Some believed they were clouds of gas inside our own galaxy. Others suspected something far larger: entire galaxies beyond the Milky Way. Using observations from the Mount Wilson Observatory in California, Hubble helped settle the question. These distant nebulae were not nearby clouds. They were enormous galaxies. Vast collections of stars, each containing millions or even billions of suns. The universe suddenly became much larger than humanity had imagined. But another discovery soon followed. And this one was even more surprising. When astronomers studied the light from distant galaxies, they noticed something unusual. The light was shifted toward the red end of the spectrum. This effect is called redshift. To understand it, it helps to think about sound. When an ambulance drives past, the pitch changes as it moves away. Light behaves in a similar way. If a galaxy moves away from us, its light stretches slightly. The wavelengths become longer. The light shifts toward red. The farther away a galaxy was, the more redshift astronomers observed. This suggested something remarkable. Galaxies were moving away from one another. The universe itself was expanding. In 1929, Hubble published observations showing a relationship between distance and recession speed. Distant galaxies appeared to move away faster than nearby ones. Not because Earth sat at the center of the universe, but because space itself was stretching. Imagine dots drawn on the surface of a balloon. As the balloon expands, every dot moves farther from every other dot. No single dot is the center of expansion on the surface itself. In a similar way, galaxies drift apart because the fabric of space expands between them. This idea changed cosmology completely. The universe was not static after all. It was dynamic, evolving, changing over time. Einstein reportedly later described the cosmological constant as his greatest blunder. He believed he had unnecessarily altered his equations to force the universe into stillness. Yet the story would become stranger decades later. Because the cosmological constant would eventually return to the center of cosmology once again. At first, the discovery of expansion was already astonishing enough. Scientists began asking new questions. If the universe is expanding today, what was it like in the past? Running the expansion backward suggested something extraordinary. Long ago, the universe must have been smaller, hotter, denser. This idea slowly developed into what we now call the Big Bang Theory. Not an explosion into empty space, but the expansion of space itself from an earlier dense state. Over billions of years, matter cooled, stars formed, galaxies emerged. Clusters of galaxies gathered across immense cosmic webs. Gravity shaped the large-scale structure of the universe. Throughout the 20th century, astronomers refined this picture carefully. Better telescopes revealed deeper regions of space. Better instruments measured light more precisely. The expanding universe became one of the foundations of modern cosmology. But an important question remained unresolved. How fast should the expansion slow down? Because gravity still matters. Every galaxy pulls on every other galaxy. Over time, gravity should resist expansion. Scientists expected the expansion rate to gradually decrease. The universe might continue expanding forever at a slower pace. Or gravity might eventually halt the expansion entirely, perhaps even reverse it. Cosmologists spent decades trying to measure this slowdown. It became one of the great scientific questions of the century. Measuring the universe is not simple. Cosmic distances are enormous. Light itself takes time to travel. Looking into deep space also means looking into the distant past. A galaxy 1 billion light-years away is seen as it existed 1 billion years ago. The deeper astronomers looked, the farther back in cosmic history they could observe. Slowly, humanity began constructing a timeline of the universe itself. During the late 20th century, astronomers developed more reliable ways to estimate vast distances. One important method involved type Ia supernovae. These are powerful stellar explosions. Under certain conditions, they reach nearly the same intrinsic brightness. Because of this consistency, astronomers can compare how bright they appear from Earth to estimate distance. These supernovae became known as standard candles. Like distant lighthouse beacons scattered across the cosmos. Teams of astronomers began studying these explosions carefully. Their goal was straightforward: measure how cosmic expansion changed over time. Most scientists expected to confirm that expansion was slowing down due to gravity. It seemed logical, natural, consistent with everything known about attractive gravitational forces. But the universe had another surprise waiting. In the 1990s, two independent research teams analyzed distant supernova data. They expected one answer. They found another. The distant supernovae appeared dimmer than expected. This meant they were farther away than predicted. The conclusion slowly became unavoidable. The expansion of the universe was not slowing down. It was accelerating. Galaxies were not merely drifting apart. Their separation was increasing faster over time. Something seemed to oppose gravity on cosmic scales. Something invisible. Something powerful. Scientists did not know what it was. But they needed a name for the phenomenon. And so the term dark energy entered modern cosmology. The word dark in this case does not mean evil or shadowy. It means unknown. Something not directly observed. Something inferred through its effects. Dark energy cannot be seen through telescopes. It does not glow like stars. It does not absorb light like dust clouds. Instead, astronomers observe the behavior of galaxies and cosmic expansion. From those observations, they infer that some form of energy or property of space itself may be driving acceleration. Today, the idea of dark energy sits at the center of cosmology. According to current models, ordinary matter makes up only a small fraction of the universe. Stars, planets, gas clouds, oceans, trees, human beings. All the visible structures we know account for only a small percentage of cosmic content. Most of the universe appears to consist of dark matter and dark energy. And dark energy may be the largest component of all. Yet, despite its importance, scientists still do not fully understand what dark energy truly is. It may be connected to the energy of empty space itself. It may involve quantum physics. Or perhaps gravity behaves differently across enormous cosmic distances. Some possibilities fit observations better than others. But no single explanation has been confirmed completely. The mystery remains open. There is something deeply humbling about this. Humanity has mapped planets, walked on the moon, measured ancient starlight from billions of years ago. And yet the largest component of the universe still remains uncertain. Modern cosmology rests partly upon an unknown, a quiet reminder that science is always evolving. The deeper we look into the cosmos, the more the universe reveals both clarity and mystery together. And before we can explore what dark energy might actually be, it helps to first understand how scientists describe the contents of the universe itself. When astronomers study the universe, they often begin with a simple question: what is everything made of? At first, the answer seems obvious. Stars, planets, dust clouds, oceans, galaxies. Everything we can see. But modern cosmology tells a very different story. The visible universe is only a small fraction of the whole. The matter that forms human beings, trees, mountains, stars, and distant galaxies accounts for only about 5% of the total cosmic energy budget. Just 5%. The remaining 95% appears to consist of things we cannot directly see: dark matter and dark energy. This realization emerged slowly over many decades. Scientists did not suddenly decide the universe was invisible. Instead, observations kept revealing inconsistencies. Galaxies rotated too quickly. Clusters of galaxies behaved strangely. The expansion of the universe accelerated unexpectedly. Again and again, the cosmos appeared to contain more than what telescopes alone could detect. To understand dark energy, it helps to separate these cosmic ingredients carefully. Ordinary matter is the easiest place to begin. Ordinary matter is made of atoms. Atoms form molecules. Molecules form planets and living things. Ordinary matter interacts with light. It can reflect light, absorb light, emit light. Because of this, astronomers can observe it directly. Telescopes collect visible light, infrared radiation, radio waves, X-rays, and other forms of electromagnetic radiation. All of these reveal different aspects of ordinary matter throughout the universe. For a long time, scientists assumed ordinary matter made up most of the cosmos. It seemed reasonable. After all, stars and galaxies dominate the night sky. But gravity revealed another story. In the 20th century, astronomers began measuring how galaxies rotate. According to Newtonian gravity, stars farther from a galactic center should orbit more slowly, similar to planets in the solar system. Mercury moves faster than Neptune because it sits closer to the Sunday. The farther away an object is, the weaker gravity becomes. But galaxies did not behave this way. Stars near the outer edges often moved unexpectedly fast. Fast enough that galaxies should have flown apart. Yet, they remained stable. Something invisible appeared to provide additional gravity. Scientists called this unseen substance dark matter. Again, the word dark simply meant invisible to telescopes. Dark matter does not appear to emit or absorb light in ordinary ways. But its gravitational influence shapes galaxies and galaxy clusters throughout the universe. Dark matter and dark energy are often confused with one another, but they are very different ideas. Dark matter behaves like matter. It exerts gravity. It helps pull structures together. Dark energy appears to do almost the opposite. It seems associated with the accelerated expansion of space itself. Instead of drawing galaxies together, dark energy contributes to their increasing separation over enormous distances. Scientists estimate that dark matter makes up roughly 27% of the universe. Dark energy may account for nearly 68%. Ordinary matter forms only a small remainder. These numbers come from multiple independent observations. Measurements of the cosmic microwave background, galaxy clustering, supernova observations, large-scale cosmic structure. Together, these observations support what is known as the lambda CDM model, the current standard model of cosmology. The name sounds technical, but each part has meaning. CDM stands for cold dark matter. Cold means the dark matter moved relatively slowly compared to the speed of light during the early universe. This helps explain how galaxies and cosmic structures formed over time. The symbol lambda refers to the cosmological constant, the same term Einstein once introduced into general relativity. In modern cosmology, lambda is often used to represent dark energy in its simplest form, a constant energy density filling space uniformly, not concentrated in galaxies, not clumped like matter. Instead, dark energy appears remarkably smooth across the universe. This smoothness is important. Matter tends to gather. Gravity pulls matter into stars and galaxies. But dark energy does not seem to cluster significantly. As space expands, dark energy remains spread throughout that expanding space. In some models, the total amount of dark energy even increases as the universe grows larger because more space itself exists. This idea feels strange at first. Yet mathematically, it matches many observations surprisingly well. One reason dark energy is difficult to understand is because it does not behave like everyday experience. Humans evolved at ordinary scales. We understand falling objects, flowing water, heat, and motion. But cosmic expansion occurs across incomprehensible distances. Galaxies separated by billions of light years are affected most strongly. On smaller scales, gravity usually dominates. The Milky Way galaxy is not being torn apart by dark energy. The solar system is not expanding noticeably. Earth is not drifting away from the sun because of dark energy. Gravity and other forces bind local systems together far more strongly. Dark energy becomes important mainly across enormous cosmic distances, over billions of years, across vast regions of intergalactic space. This makes it difficult to observe directly. Scientists must study large populations of galaxies and deep cosmic history to infer its effects. There is another reason the subject feels difficult. The term energy itself can be misleading. In daily life, energy often means motion or fuel. Electricity powering a city, food fueling the body. But in physics, energy has a broader meaning. It describes the capacity associated with physical systems and fields. Dark energy may not resemble anything familiar from ordinary human experience. scientists still debate the true nature of dark energy. Some interpretations describe it as vacuum energy, energy inherent to empty space itself. Others explore dynamic fields that evolve over time. Some researchers even question whether general relativity behaves differently at the largest scales in the universe. The mystery remains active and unresolved. This uncertainty is important to understand clearly. In science, not knowing something is not failure. It is part of the process. Cosmologists openly acknowledge that dark energy remains one of the biggest unanswered questions in physics. The evidence for accelerated expansion is strong. But the deeper explanation behind it is still being explored. Sometimes popular discussions create the impression that scientists fully understand the universe already. But modern cosmology contains profound uncertainties. The equations describing cosmic evolution work remarkably well. Yet some of the largest components inside those equations remain mysterious. Humanity can model the expansion history of the universe with extraordinary precision. But explaining why dark energy exists at all is far more difficult. There is a quiet humility in this situation. The observable universe contains hundreds of billions of galaxies. Each galaxy may contain billions of stars. And most of the cosmos appears to consist of phenomena still not fully understood. Modern astronomy reveals both knowledge and uncertainty together. Over time, scientists have built increasingly sensitive instruments to study these mysteries. Space telescopes observe ancient light from the early universe. Giant surveys map the distribution of galaxies across billions of light-years. Satellites measure tiny fluctuations in cosmic radiation left behind from the early universe. Every new observation adds another piece to the puzzle. Yet the central question remains remarkably simple. Why is the expansion of the universe accelerating? What property of nature causes this behavior? Is dark energy truly constant? Or could it change slowly over time? Could the answer lie within quantum physics or within gravity itself? At present, no one knows with certainty. Interestingly, the story of dark energy also circles back to Einstein. Decades before the discovery of cosmic acceleration, he had already introduced a mathematical term that resembled the effects now associated with dark energy. At the time, he used it for a very different reason. But modern cosmology would eventually return to that same idea in an unexpected way. And to understand why, it helps to look more closely at Einstein's equations and the strange history of the cosmological constant itself. In the early 20th century, physics was changing rapidly. Old assumptions about space, time, and gravity were beginning to break apart. At the center of this transformation was a physicist named Albert Einstein. Einstein had already introduced the special theory of relativity in 1905. That theory changed how scientists understood motion and time. It showed that measurements of time and distance depend on relative motion between observers. It also revealed something profound. Space and time are deeply connected. Together, they form a unified structure called spacetime. But special relativity did not fully describe gravity. Newton's law of gravity had worked extremely well for centuries. It explained falling apples, planetary motion, and the paths of comets. Yet Einstein believed gravity required a deeper explanation. After years of difficult work, he completed the general theory of relativity in 1915. General relativity described gravity not as a force pulling objects through space, but as the curvature of spacetime itself. Massive objects distort the geometry around them. Planets and stars move along paths shaped by that curvature. A common analogy compares spacetime to a stretched fabric. If a heavy ball rests on the fabric, the surface bends. Smaller objects rolling nearby follow curved paths around the depression. The analogy is imperfect, but it helps visualize the idea. Gravity emerges from geometry itself. Einstein's equations were extraordinarily powerful. They correctly explained subtle features of Mercury's orbit that Newtonian gravity could not fully account for. They predicted the bending of light near massive objects. They predicted gravitational time dilation. Over the following decades, observation after observation confirmed the theory with remarkable precision. But Einstein soon noticed something troubling hidden inside his equations. When applied to the universe as a whole, the equations suggested that the cosmos could not remain perfectly static. Gravity causes attraction. Matter pulls matter together. A universe filled with matter should either contract inward or expand outward over time. A perfectly motionless universe appeared unstable. This was uncomfortable for Einstein. Like many scientists of his era, he believed the universe was eternal and largely unchanging on the largest scales. The idea of a dynamic universe seemed strange. There was little observational evidence yet suggesting otherwise. So Einstein modified his equations. He introduced an additional mathematical term called the cosmological constant, represented by the Greek letter lambda. This extra term acted as a kind of repulsive effect within spacetime. On large scales, it could counterbalance gravity. If adjusted carefully, the cosmological constant allowed for a static universe. The idea was mathematically elegant in some ways, but the balance was delicate. Too much attraction and the universe collapses. Too much repulsion and the universe expands. Einstein fine-tuned the cosmological constant to maintain stability. Yet the solution was unstable in practice. Even small disturbances could upset the balance. Meanwhile, other physicists were exploring Einstein's equations independently. One of them was the Russian physicist Alexander Friedmann. In the early 1920s, Friedmann discovered solutions to Einstein's equations that described an expanding or contracting universe naturally. A dynamic cosmos emerged directly from general relativity itself. At first, Einstein believed Friedmann had made mistakes. Later, he acknowledged the mathematics was correct. Around the same period, the Belgian physicist and priest Georges Lemaitre reached similar conclusions. Lemaitre proposed that the universe might be expanding from an earlier dense state. His ideas anticipated important aspects of what later became the Big Bang model. Then came the observations of Edwin Hubble. During the 1920s, Hubble measured the redshifts of distant galaxies and showed that galaxies generally move away from one another. The farther away a galaxy appeared, the faster it receded. The universe was expanding. Suddenly, the cosmological constant no longer seemed necessary to force a static universe. The observations already matched the natural expanding solutions of general relativity. Einstein reportedly became dissatisfied with his earlier modification. According to later accounts, he referred to the cosmological constant as his greatest blunder. Historians debate the exact wording and context of that statement. But the broader idea reflects Einstein's regret. He believed he had complicated his equations unnecessarily because of an incorrect assumption about the universe being static. For many decades afterward, the cosmological constant faded into the background of cosmology. Most scientists focused on a universe shaped primarily by matter and gravity. The central question became how expansion changes over time under gravitational attraction. Would the universe expand forever? Or would gravity eventually reverse the expansion? Throughout much of the 20th century, cosmologists generally expected expansion to slow gradually. After all, gravity is attractive. Galaxies pull on one another. Large amounts of matter should resist cosmic expansion over immense timescales. The only uncertainty seemed to be how quickly the slowing occurred. Then, late in the century, observations revealed something unexpected. The expansion was not slowing down. It was accelerating. This result surprised the scientific community deeply. Cosmologists now faced a difficult problem. What could drive accelerated expansion across the universe? Ordinary matter could not explain it. Gravity alone should oppose expansion, not strengthen it. And suddenly, Einstein's abandoned cosmological constant became relevant again. The mathematical term once introduced to stabilize the universe now resembled the behavior needed to explain acceleration, a repulsive property associated with spacetime itself, something capable of overcoming gravity on enormous scales. Modern cosmology often describes dark energy using this cosmological constant framework. In this interpretation, empty space possesses a small but persistent energy density. As the universe expands, that energy continues filling space uniformly. Over billions of years, its effects become increasingly important. One reason this idea works mathematically is because of how pressure behaves in general relativity. In Einstein's theory, not only mass but also pressure contributes to the curvature of spacetime. Ordinary matter has positive pressure or negligible pressure. But the cosmological constant behaves differently. It effectively produces negative pressure. This negative pressure contributes to accelerated expansion. The concept feels unusual because negative pressure is not part of ordinary daily experience. Yet mathematically, it emerges naturally within the equations of general relativity. Space itself can possess properties that influence cosmic evolution. Even so, important questions remain unresolved. If dark energy truly corresponds to vacuum energy associated with empty space, why is its value so small? Quantum physics predicts vacuum energy contributions vastly larger than what astronomers observe. The discrepancy is enormous. One of the largest known mismatches between theory and observation in all of science. This issue is sometimes called the cosmological constant problem. Physicists still do not understand why the observed acceleration corresponds to such a tiny value compared to naive theoretical expectations. The equations work. The observations fit remarkably well. But the deeper explanation remains unclear. Some scientists therefore suspect the cosmological constant may not be the full answer. Perhaps dark energy changes slowly over time. Perhaps additional fields exist throughout the universe. Perhaps gravity itself behaves differently at enormous scales. Many possibilities continue to be explored. Yet, despite these uncertainties, Einstein's equations remain central to modern cosmology. More than a century after general relativity was published, the theory still describes gravitational phenomena with extraordinary accuracy. Black holes, gravitational lensing, gravitational waves, cosmic expansion. Again and again, observations confirm the power of the theory. There is something quietly remarkable about this history. A mathematical term Einstein, once introduced reluctantly, later became one of the leading explanations for one of the universe's greatest mysteries. A correction designed to preserve a static cosmos eventually helped describe an accelerating one. Science often moves this way. Ideas change meaning over time. Equations developed for one purpose later illuminate entirely different discoveries. Understanding deepens gradually through observation, revision, and careful questioning. And as astronomers continued measuring distant galaxies with greater precision, the evidence for cosmic acceleration became stronger and harder to ignore. By the late 20th century, astronomers had already accepted that the universe was expanding. That much was clear. Galaxies drifted apart across immense cosmic distances. The discovery traced back to Edwin Hubble and the redshift observations of the 1920s. But another question remained unresolved. How was the expansion changing over time? Most scientists expected gravity to slow the expansion gradually. Matter attracts matter. Galaxies pull on one another through gravity. Over billions of years, this attraction should resist outward motion. The universe might still expand forever, but more slowly with time. Or perhaps gravity would eventually halt expansion entirely and reverse it. To answer this question, astronomers needed a way to measure enormous cosmic distances accurately. This is much harder than measuring distances on Earth. In daily life, distance can be measured directly. A ruler, a road sign, a satellite signal. But galaxies are unimaginably far away. Their light travels for millions or billions of years before reaching Earth. Astronomers therefore rely on what is called the cosmic distance ladder, a series of overlapping methods used to estimate distances progressively farther into space. Nearby distances can be measured through parallax. More distant stars require other techniques. Galaxies farther away require still different methods. One of the most important tools in this effort became a special kind of exploding star called a Type Ia supernova. These supernovae occur under specific conditions involving white dwarf stars. A white dwarf is the dense remnant left behind after a sun-like star exhausts its nuclear fuel. Though small in size, white dwarfs contain large amounts of mass packed tightly together. In some binary star systems, a white dwarf pulls matter from a nearby companion star. As material accumulates, the white dwarf approaches a critical mass limit called the Chandrasekhar limit. Once this threshold is crossed, runaway nuclear reactions ignite suddenly. The star explodes with enormous brightness. What makes Type Ia supernovae especially useful is their consistency. Because these explosions occur near a similar mass threshold, their intrinsic brightness is relatively uniform. Astronomers can therefore estimate distance by comparing how bright a supernova truly is to how bright it appears from Earth. A brighter appearance suggests a closer object. A dimmer appearance suggests a greater distance. This method transformed cosmology. Type Ia supernovae became known as standard candles, reliable markers scattered across the cosmos. By observing these explosions in distant galaxies, astronomers could probe the expansion history of the universe itself. During the 1980s and 1990s, two major research teams focused intensely on this effort: the Supernova Cosmology Project and the High-Z Supernova Search Team. Their goal was straightforward: measure distant supernovae carefully enough to determine whether cosmic expansion was slowing down. The work required patience. Supernovae are temporary events. Astronomers had to search large regions of sky repeatedly. They compared images taken at different times, looking for new points of light appearing in distant galaxies. Once detected, the supernovae had to be studied quickly before they faded. This involved international collaboration. Telescopes across the world collected data. Spectra measured redshift. Brightness curves were analyzed carefully. Corrections accounted for dust, instrumental effects, and subtle variations among explosions. Cosmology was becoming increasingly precise. At first, many researchers expected the results to confirm a slowing universe. The debate focused mainly on how much matter existed in the cosmos. More matter would produce stronger gravitational slowing. Less matter would allow expansion to continue more easily. But few expected acceleration. Then the data began pointing somewhere unexpected. Distant supernovae appeared dimmer than anticipated. Dimmer meant farther away. Farther away meant the universe had expanded more than predicted. Slowly, a remarkable conclusion emerged. The expansion of the universe was accelerating. Not merely continuing, accelerating. Galaxies were becoming separated at an increasing rate over time. Something appeared to oppose gravity across the cosmos. Something invisible and pervasive. The discovery was announced in 1998. It quickly became one of the most important findings in modern cosmology. The implications were enormous. Scientists now needed to explain why the universe behaved this way. One possibility immediately stood out: Einstein's cosmological constant. The mathematical term, once introduced to stabilize the universe, suddenly resembled the behavior required to drive acceleration. A small energy associated with spacetime itself, uniformly distributed across the cosmos. Over time, this idea became central to the standard cosmological model. The simplest explanation for dark energy is still the cosmological constant, a constant vacuum energy filling space. Yet, despite the mathematical success of the model, the deeper physical explanation remains uncertain. Importantly, the acceleration is not like galaxies flying outward through empty space after an explosion. The expansion occurs because space itself stretches. This distinction matters. Galaxies are generally not racing through a pre-existing void. Instead, the distances between galaxies increase as space-time expands. A common analogy involves dots drawn on the surface of an inflating balloon. As the balloon expands, each dot moves farther from the others. No dot needs to move across the surface actively. The surface itself changes. Likewise, cosmic expansion reflects changing geometry across spacetime. This expansion also affects light traveling through the universe. As space stretches, wavelengths of light stretch too. This produces cosmological redshift. The farther light travels through expanding space, the more its wavelength increases. Observing this redshift allows astronomers to trace cosmic expansion across billions of years. The farther astronomers look into space, the farther back in time they observe. Light from distant galaxies began its journey long before Earth existed in its present form. Some photons reaching telescopes tonight started traveling billions of years ago. Deep cosmology is also deep history. The accelerating universe, therefore, tells a story unfolding across cosmic time. Early in the universe's history, matter was denser. Gravity dominated more strongly. Expansion slowed during those earlier eras. But as space continued expanding, matter became increasingly spread out. The influence of dark energy gradually became more important. Around 5 billion years ago, dark energy appears to have begun dominating the large-scale behavior of the universe. Since then, acceleration has shaped cosmic evolution increasingly strongly. Galaxies continue drifting farther apart. Clusters separate slowly across vast distances. The discovery of acceleration also strengthened the importance of precision cosmology. Scientists combined supernova observations with other measurements. The cosmic microwave background, galaxy surveys, large-scale structure. Together, these independent methods converged on a remarkably consistent picture. A universe dominated not by ordinary matter, but by dark matter and dark energy. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Their work reshaped cosmology permanently. Yet the discovery also deepened the mystery. Measuring acceleration is not the same as explaining it. Observations reveal what the universe is doing. Understanding why remains much harder. The simplest models treat dark energy as constant, unchanging across time and space. But some researchers wonder whether dark energy evolves slowly. Others question whether gravity itself changes behavior over immense cosmic distances. Many possibilities remain open. Even now, astronomers continue refining supernova measurements with greater precision. New telescopes observe larger samples across deeper regions of the universe. Statistical uncertainties shrink gradually. Small tensions between measurements are studied carefully. The expansion history of the cosmos remains an active field of research. There is something quietly profound about this method of discovery. Tiny points of light, appearing briefly in distant galaxies, revealed that space-time itself behaves differently than expected. Fleeting stellar explosions helped uncover one of the deepest mysteries in physics. And as scientists searched for explanations, attention increasingly turned toward the strange possibility that even empty space might contain energy of its own. One of the strangest ideas in modern physics is that empty space may not truly be empty. At first, this sounds impossible. Empty space appears to contain nothing at all. No stars, no planets, no gas clouds. Just darkness stretching between galaxies. But physics describes emptiness differently than everyday intuition. According to modern quantum theory, even a vacuum possesses structure and activity at extremely small scales. Space itself may contain energy. This possibility became one of the leading explanations for dark energy. The idea is known as vacuum energy. To understand why physicists take this idea seriously, it helps to step slowly into the world of quantum mechanics. Quantum theory describes nature at the smallest known scales. Atoms, electrons, subatomic particles. And unlike ordinary human experience, the quantum world behaves in ways that often seem deeply unfamiliar. In classical physics, a vacuum is simple. Remove all matter and radiation from a region of space, and nothing remains. A perfectly empty container. But quantum physics does not allow perfect stillness so easily. Fields exist throughout space. According to quantum field theory, particles are excitations of underlying fields that permeate the universe. The electron field exists everywhere. The electromagnetic field exists everywhere. Even in regions where no particles are present, these fields remain. Quantum systems also possess uncertainty built into nature itself. Werner Heisenberg's uncertainty principle describes limits on how precisely certain quantities can be known simultaneously. Position and momentum, for example. Energy and time also participate in related uncertainty relationships. Because of these quantum effects, fields cannot remain perfectly motionless. Tiny fluctuations persist, even in vacuum conditions. Physicists sometimes describe this as quantum foam or vacuum fluctuations. At incredibly small scales, the vacuum behaves less like absolute emptiness and more like a restless background. One way to visualize this involves virtual particles. In simplified descriptions, pairs of particles and antiparticles briefly appear and disappear within vacuum fluctuations. These are not ordinary particles moving freely through space. Rather, they emerge mathematically within quantum field calculations. The language is imperfect, but it helps convey the idea that quantum vacuums are not completely inactive. Importantly, vacuum fluctuations are not merely philosophical speculation. Their effects can be measured experimentally. One famous example is the Casimir effect. When two extremely close metal plates are placed near one another in vacuum conditions, quantum fluctuations create a tiny measurable force between them. This demonstrates that vacuum states possess physical properties. Once physicists realized vacuum energy might be real, an intriguing possibility emerged. Perhaps the energy of empty space contributes to cosmic expansion. Perhaps dark energy is vacuum energy itself. This idea fits naturally with Einstein's cosmological constant. A constant energy density filling all of space could drive accelerated expansion. Empty space would not truly be empty. Instead, space-time itself would contain intrinsic energy. As the universe expands, more space exists. If vacuum energy density remains constant, then total vacuum energy increases as space grows larger. Over billions of years, this effect becomes cosmologically important. Matter becomes diluted as expansion spreads galaxies farther apart. But vacuum energy remains persistent throughout space itself. Eventually, vacuum energy dominates cosmic evolution. Expansion accelerates. Galaxies drift apart more rapidly across immense distances. Mathematically, this explanation works surprisingly well. Observations of supernovae, galaxy clustering, and the cosmic microwave background align closely with a cosmological constant model. The simplest version of dark energy remains highly successful observationally. Yet beneath this success lies one of the deepest problems in theoretical physics: the cosmological constant problem. The problem begins when physicists attempt to calculate vacuum energy using quantum field theory. Quantum fields contain fluctuations across many possible energy modes. When theorists estimate the vacuum energy contribution from these fluctuations, the result becomes extraordinarily large, vastly larger than the amount of dark energy actually observed astronomically. The mismatch is difficult to overstate. Depending on calculation methods and assumptions, theoretical predictions exceed observational values by roughly 10 to the power of 120, a 1 followed by 120 zeros. This is sometimes described as the worst theoretical prediction in physics. Not because the mathematics is careless, but because quantum theory and cosmological observations appear profoundly disconnected here. The observed dark energy density is extremely small, and yet even a tiny positive vacuum energy becomes significant across cosmic scales because space itself is enormous. Over billions of light years, small effects accumulate. Physicists have proposed many ideas to explain this discrepancy. Some hope unknown symmetries cancel most vacuum energy contributions. Others explore multiverse scenarios in which many possible vacuum states exist. Some suggest our understanding of quantum gravity remains incomplete. No widely accepted solution currently exists. The challenge reveals something important about modern physics. General relativity describes gravity and cosmic expansion extremely well. Quantum field theory describes subatomic particles with extraordinary precision. Yet combining these frameworks fully remains one of science's greatest unfinished tasks. Dark energy may therefore point toward deeper physics still undiscovered. The accelerating universe could be revealing limitations in current theories. A clue hidden within cosmic expansion itself. Despite these unresolved questions, vacuum energy remains an important concept because it arises naturally from known physics. Quantum fields already exist within modern theory. Vacuum fluctuations already produce measurable effects. The mystery lies not in whether quantum vacuums exist, but in why their large-scale energy behaves the way observations suggest. There is also an interesting philosophical shift here. Ancient ideas often imagined empty space as simple nothingness. Modern physics describes emptiness as structured and active. Even regions between galaxies may participate in cosmic evolution. Yet it is important not to drift into mystical interpretations. Vacuum energy emerges from mathematical models and observational evidence, not supernatural concepts. Physicists study these ideas carefully through equations, experiments, and astronomical observations. The universe often behaves in ways that differ from everyday intuition. Quantum mechanics already demonstrated this repeatedly during the 20th century. Particles behave like waves. Probabilities shape outcomes. Empty space fluctuates. Dark energy may be another example of nature operating beyond ordinary human expectations. Some physicists remain cautious about identifying dark energy directly with vacuum energy. After all, the cosmological constant problem remains unresolved. If theoretical predictions fail so dramatically, perhaps the full explanation lies elsewhere. This uncertainty has encouraged alternative ideas. Maybe dark energy is not constant. Maybe it changes slowly over time. Perhaps an entirely new field exists throughout the universe, evolving across cosmic history. In these models, dark energy behaves less like fixed vacuum energy and more like a dynamic component of the cosmos. A field capable of changing strength gradually as the universe evolves. These possibilities led cosmologists toward another idea with an ancient name: quintessence. And unlike the cosmological constant, quintessence would allow dark energy itself to evolve over time as the universe expands. The simplest explanation for dark energy is the cosmological constant, a fixed energy density woven into space itself. Constant across time, constant across the universe. But some physicists wonder whether dark energy might be more dynamic than that. Perhaps it changes slowly over cosmic history. Perhaps the acceleration of the universe is driven not by a constant property of empty space, but by a field evolving over time. One major class of these ideas is called quintessence. The name comes from ancient philosophy. In medieval thought, Quintessence referred to a hypothetical fifth element beyond Earth: water, air, and fire. Modern cosmology uses the term very differently. Here, quintessence refers to a proposed scalar field permeating the universe. Scalar fields already play important roles in physics. A scalar field assigns a value to every point in space and time. Temperature across a room is a simple, everyday example of a scalar field. Each location has a temperature value. In fundamental physics, scalar fields appear in quantum field theory as well. The Higgs field is one famous example. Particles interacting with the Higgs field acquire mass through those interactions. Quintessence proposes another field spread throughout the cosmos. But unlike a constant vacuum energy, this field can evolve gradually over time. Its energy density may shift as the universe expands. This distinction matters. In cosmological constant models, dark energy remains fixed. The acceleration of the universe follows from that constant background energy. But in quintessence models, the strength of dark energy can vary slowly across cosmic history. Some quintessence models predict acceleration that changes gently over billions of years. Others allow dark energy to become stronger or weaker, depending on how the field evolves. In certain scenarios, dark energy might eventually fade almost entirely. In others, acceleration continues indefinitely. To understand why fields can produce acceleration, it helps to think about energy and pressure in cosmology. In general relativity, pressure influences spacetime dynamics alongside energy density. Quintessence fields can generate negative pressure under certain conditions. This negative pressure contributes to accelerated expansion. The details involve mathematical equations describing how the field evolves over time. These equations depend on something called a potential energy function. The field moves through this potential somewhat like a ball rolling across a landscape. Different landscapes produce different cosmic behaviors. If the field changes slowly enough, its energy behaves similarly to dark energy observed today. The universe accelerates gently over immense timescales. One appealing feature of quintessence is flexibility. Because the field evolves dynamically, some models may reduce the fine-tuning problems associated with the cosmological constant. Physicists hoped dynamic fields might help explain why dark energy appears so small yet non-zero. However, quintessence introduces new challenges as well. The field itself has never been directly observed. Scientists must infer its possible existence indirectly through cosmological measurements. And many different mathematical models are possible. Some quintessence scenarios predict subtle variations in the expansion history of the universe. Others affect the growth of cosmic structures such as galaxies and galaxy clusters. Astronomers search for these signatures carefully. Observations so far still remain broadly consistent with the simpler cosmological constant picture. That does not rule out quintessence entirely, but it means any evolving dark energy field must behave in ways closely resembling a cosmological constant today. Measuring these tiny differences is extremely difficult. The universe evolves across billions of years. Dark energy itself appears weak compared to local forces. Its effects emerge mainly across enormous cosmic distances and timescales. Large astronomical surveys therefore become essential. Scientists map millions of galaxies. They measure redshifts precisely. They study how cosmic structure evolved over time. Tiny deviations from standard predictions may reveal clues about whether dark energy changes slowly. Some recent observations have even hinted at slight tensions within the standard cosmological model. These hints remain uncertain and actively debated. Statistical noise, measurement errors, or unknown systematic effects may explain them. But they continue motivating research into evolving dark energy scenarios. Quintessence also connects cosmology to broader questions in particle physics. If such a field exists, where did it come from? Did it emerge during the early universe? Does it interact weakly with other particles? Why is its energy scale so small compared to other known forces in physics? These questions remain unanswered. Yet they illustrate something important about modern cosmology. The universe is not studied as separate, isolated subjects anymore. Gravity, particle physics, quantum theory, and cosmic evolution are deeply connected. Dark energy sits at the intersection of all these fields. Understanding it may require entirely new physics. There is also an interesting historical parallel here. Earlier generations of astronomers believed the universe was static because large-scale cosmic change was difficult to observe directly. Later, observations revealed expansion. Then observations revealed acceleration. Now scientists ask whether the acceleration itself changes over time. Cosmology continues becoming more precise. Questions once considered impossible to test gradually move into observational science. Some quintessence models predict something called tracker behavior. In these scenarios, the field naturally evolves towards certain behaviors regardless of its precise starting conditions. This could potentially explain why dark energy becomes important only during relatively recent cosmic history. Without such mechanisms, some cosmologists worry about coincidence problems. Why does dark energy begin dominating around the same era when galaxies and observers like humans exist? Is this timing meaningful, or merely observational coincidence? Different physicists approach these questions differently. Some favor minimal explanations with fewer assumptions. Others explore richer theoretical frameworks, hoping to uncover deeper patterns hidden within cosmology. Importantly, quintessence remains hypothetical. No direct evidence currently proves such a field exists. The cosmological constant still provides the simplest explanation, matching most observations. Yet the possibility of evolving dark energy remains scientifically valuable because it is testable. Future observations may eventually distinguish between constant and dynamic dark energy models. Precise measurements of cosmic expansion history could reveal whether dark energy changes subtly over time. New galaxy surveys and space telescopes are designed partly for this purpose. There is something quietly fascinating about the scale of these investigations. Tiny fluctuations in distant starlight, subtle patterns among galaxies, slight shifts in expansion rates. From these delicate signals, scientists attempt to understand the fate of the entire universe. Yet some researchers take an even more radical position. Perhaps dark energy does not exist at all. Perhaps the real issue lies elsewhere. Maybe gravity itself behaves differently across the largest cosmic scales. And if that is true, the mystery of cosmic acceleration may require rewriting part of our understanding of gravity itself. For more than a century, general relativity has remained one of the most successful scientific theories ever developed. Einstein's equations describe gravity with extraordinary accuracy. They correctly predict the motion of planets, the bending of light, the existence of black holes, gravitational waves. Again and again, observations confirm the theory. And yet, some physicists wonder whether general relativity may still be incomplete, not wrong in ordinary conditions, but perhaps incomplete on the very largest scales in the universe. This idea leads to a different possibility for explaining cosmic acceleration. Maybe dark energy does not exist at all. Maybe the universe only appears to accelerate because gravity behaves differently across enormous cosmic distances. In this view, the mystery lies not in some hidden energy filling space, but in gravity itself. To understand why scientists consider this possibility, it helps to remember how theories evolve in physics. Newton's theory of gravity worked remarkably well for centuries. It explained planetary motion with great precision. But eventually, tiny discrepancies appeared. The orbit of Mercury behaved slightly differently than Newtonian gravity predicted. Then Einstein introduced general relativity, revealing gravity as curved spacetime rather than an invisible force acting instantly across space. Newton was not simply discarded. His equations still work extremely well in many situations. But Einstein's theory expanded the picture. Some cosmologists now ask whether something similar could happen again. Perhaps general relativity works perfectly at solar system scales, yet changes subtly across billions of light years. This possibility has inspired many modified gravity theories. These theories attempt to explain cosmic acceleration without invoking dark energy as a separate substance or field. Instead, the equations governing spacetime themselves are adjusted. One broad category involves modifying Einstein's gravitational equations directly. In standard general relativity, spacetime curvature responds to matter and energy according to a specific mathematical relationship. Modified gravity models alter parts of this relationship, sometimes by adding new terms, sometimes by introducing additional fields, sometimes by changing how curvature behaves at extremely large scales. One example is called FR gravity. In these models, the equations depend on more complicated functions of spacetime curvature than Einstein originally proposed. Under certain conditions, these modified equations can produce accelerated expansion naturally. Another family of ideas involves extra dimensions. Some theories, inspired by string theory, suggest the universe may contain more spatial dimensions than humans perceive directly. Gravity could behave differently if extra dimensions influence space-time geometry across vast scales. In some models, gravity leaks into these additional dimensions, weakening its behavior over cosmic distances and altering expansion. There are also theories involving massive gravity. In Einstein's theory, gravity is mediated by spacetime geometry without requiring a massive carrier particle. Some modified gravity models instead explore the possibility that gravitational interactions behave as though associated with particles possessing tiny masses. This changes how gravity operates across large distances. Each of these ideas attempts to explain the same observations differently. Galaxies appear to separate faster over time. But instead of attributing this behavior to dark energy, modified gravity theories reinterpret the underlying cause. Importantly, these theories are not invented randomly. They arise from mathematical attempts to reconcile cosmology, gravity, and quantum theory more completely. Some physicists suspect general relativity and quantum mechanics may ultimately require a deeper unifying framework. Dark energy could therefore be a symptom of incomplete gravitational theory rather than a new cosmic substance. However, modifying gravity is difficult. General relativity has passed many experimental tests with extraordinary precision. Any replacement or extension must reproduce all those successful predictions while also explaining cosmic acceleration. This creates strong constraints. For example, modified gravity theories must still correctly describe planetary orbits, gravitational lensing, black hole behavior, and gravitational waves. Even tiny inconsistencies can rule out proposed models. In recent years, gravitational wave astronomy has become especially important here. When observatories such as LIGO detected gravitational waves traveling across the universe, scientists gained new ways to test gravity directly. Some modified gravity theories predicted gravitational waves should behave differently from Einstein's theory. Observations have already eliminated certain possibilities. This illustrates how cosmology increasingly depends on multiple forms of evidence working together. Galaxy surveys, supernova observations, cosmic microwave background measurements, gravitational waves. Each provides different tests of cosmic models. So far, the standard cosmological model with dark energy remains highly successful overall. No modified gravity theory has yet replaced it convincingly. But the search continues because important conceptual problems remain unresolved. Some physicists feel uneasy about introducing a mysterious dark energy component comprising most of the universe without understanding its fundamental origin. Others argue that modifying gravity may create even greater theoretical complications. The scientific discussion remains active and thoughtful. There is something deeply human in this process. Science advances not only through answers, but through uncertainty. Researchers test assumptions repeatedly. They question whether existing theories apply under all conditions. They search for simpler explanations when mysteries appear. Cosmology especially encourages this humility. The observable universe spans roughly 93 billion light-years in diameter. Human beings occupy a tiny region within it. The laws governing such immense scales may contain subtleties still undiscovered. At the same time, It is important not to misunderstand what scientists mean when they discuss modifying gravity. These are not arbitrary guesses. Modified gravity theories involve rigorous mathematics and observational testing. Most proposed models ultimately fail because they conflict with data. That failure is part of science working properly. Occasionally, people ask whether dark energy means scientists are making things up. But this misunderstands how cosmology operates. The observations themselves are real. Galaxies genuinely appear to separate faster over time. The question is how best to explain those observations mathematically and physically. Dark energy is one explanation. Modified gravity is another category of explanations. Scientists compare predictions carefully against evidence. In many ways, this situation resembles earlier moments in scientific history. Unexpected observations forced humanity to revise long-held assumptions repeatedly. Earth was not the center of the cosmos. Space and time were not absolute. Galaxies existed beyond the Milky Way. The universe was expanding. Dark energy may represent another turning point. Or perhaps it points toward new gravitational physics not yet fully understood. Some modified gravity theories also predict subtle differences in how cosmic structures form over time. Gravity influences how galaxies cluster together. If gravity changes at large scales, the growth of cosmic structure changes too. Astronomers, therefore, study galaxy distributions carefully, searching for patterns that might distinguish dark energy from modified gravity. Future observations may provide clearer answers. Larger galaxy surveys, better gravitational wave measurements, more precise cosmological maps. These tools may eventually reveal whether cosmic acceleration arises from dark energy, modified gravity, or something even more unexpected. For now, the mystery remains open. And regardless of which explanation ultimately proves correct, the universe continues evolving across immense stretches of time. Gravity gathers matter into galaxies and stars. Dark energy, or cosmic expansion, pulls structures apart across the largest scales. The cosmos itself exists within a quiet balance between attraction and expansion. For most of human history, people assumed the night sky was largely permanent. Stars rose and set. Constellations returned season after season. The heavens appeared calm and unchanging. Modern cosmology revealed something very different. The universe evolves continuously across immense stretches of time. Galaxies form. Stars ignite. Black holes grow. Space expands. And dark energy appears to shape the long-term future of everything. Once scientists realized cosmic expansion was accelerating, a new question naturally followed. What happens next? The answer depends strongly on the nature of dark energy itself. If dark energy remains constant, the universe may continue expanding forever at an accelerating rate. If dark energy changes over time, other futures become possible. Cosmologists study these possibilities carefully using mathematical models of cosmic evolution. These models combine observations, general relativity, thermodynamics, and particle physics to explore how the universe may behave over unimaginable timescales. One of the leading scenarios is sometimes called the heat death of the universe. The name sounds dramatic, but the process itself is gradual and quiet. Not explosive, not sudden. A slow fading across trillions upon trillions of years. To understand heat death, it helps to think about energy and entropy. Entropy is often described as a measure of disorder, though physicists define it more precisely in terms of the number of microscopic arrangements available to a system. The second law of thermodynamics states that entropy tends to increase over time in isolated systems. In practical terms, energy naturally spreads out. Heat flows from warmer regions toward cooler ones. Concentrated energy becomes more diffuse. The universe began in an extremely hot and dense state. Over billions of years, expansion allowed matter to cool and organize into galaxies, stars, and planets. Yet the overall trend toward increasing entropy continues. Stars shine because nuclear fusion converts concentrated fuel into radiation. But stars do not last forever. Eventually, hydrogen supplies become exhausted. Stellar evolution transforms stars into white dwarfs, neutron stars, or black holes depending on their masses. New stars continue forming today because galaxies still contain clouds of gas. But over immense timescales, available star-forming material gradually declines. Future galaxies may become darker and quieter. If cosmic acceleration continues indefinitely, distant galaxies will drift farther apart over time. Eventually, many galaxies beyond our local group may recede so rapidly due to expansion that their light can no longer reach us. The observable universe would gradually become emptier from any single vantage point. Trillions of years into the future, star formation may largely cease. Existing stars slowly burn out. White dwarfs cool. Neutron stars fade. Black holes remain among the last major structures. Even black holes are not truly eternal, according to modern theoretical physics. Stephen Hawking showed that quantum effects near black hole event horizons allow black holes to emit tiny amounts of radiation over immense timescales. This process is now called Hawking radiation. Extremely massive black holes evaporate extraordinarily slowly. The largest may survive for timescales vastly longer than the current age of the universe. Yet, eventually, even they may disappear through gradual evaporation. In the heat death scenario, the universe approaches a state of maximum entropy. Energy becomes spread thinly across enormous expanding space. Few organized structures remain. Temperatures approach near uniformity. Physical processes capable of sustaining complex activity become increasingly rare. Importantly, heat death does not mean everything suddenly freezes at once. It describes a long-term thermodynamic trend. The universe gradually becomes less active over incomprehensibly long durations. Yet heat death is only one possibility. Other scenarios emerge if dark energy behaves differently. One famous alternative is called the Big Rip. In certain hypothetical models, dark energy grows stronger over time instead of remaining constant. If acceleration increases rapidly enough, expansion could eventually overwhelm not only galaxies, but galaxy clusters, solar systems, planets, and ultimately atoms themselves. The sequence would unfold gradually at first. Galaxies separate faster. Clusters disperse. Later, gravitationally bound systems become unstable. In the final stages, molecular and atomic structures could theoretically be disrupted if expansion became extreme enough. However, it is important to emphasize that current observations do not strongly support a Big Rip scenario. Most evidence remains consistent with dark energy behaving approximately like a cosmological constant. Another possibility is the Big Crunch. In this scenario, cosmic expansion eventually reverses. Gravity overcomes expansion, causing the universe to contract inward. Temperatures and densities rise again over time. Earlier in cosmological history, many scientists considered this possibility seriously because the amount of matter in the universe was uncertain. But accelerated expansion makes a future collapse appear less likely under current observations. Some speculative models even explore cyclic universes. Expansion followed by contraction. Repeated cosmic eras unfolding across unimaginable timescales. These ideas remain highly theoretical and lack strong observational support today. What makes these future scenarios scientifically meaningful is that they arise from measurable physical parameters. The density of matter, the geometry of spacetime, the behavior of dark energy. Small differences in these quantities can shape the long-term evolution of the cosmos dramatically. Cosmologists, therefore, attempt to measure dark energy with increasing precision. If its strength changes even slightly over time, the ultimate fate of the universe could differ significantly from current expectations. There is something quietly humbling about these timescales. Human civilization occupies only a tiny fraction of cosmic history. Modern humans have existed for roughly a few 100,000 years. The universe itself is about 13.8 billion years old. Future cosmic evolution may continue for trillions or vastly more years beyond the present era. Even stars themselves are temporary structures within this larger timeline. Galaxies, too, may slowly fade into darkness. Cosmic expansion stretches spacetime continuously across the deep future. And yet, despite these enormous scales, the laws governing the cosmos appear mathematically coherent. Tiny fluctuations in the early universe grew into galaxies. Gravity shaped stars and planets. Chemistry produced life. Conscious beings emerged capable of studying the universe itself. Modern cosmology, therefore, carries both scientific and philosophical weight. Questions about dark energy are not merely technical calculations. They connect to deeper questions about origin, structure, and destiny. Still, scientists remain careful not to overstate certainty. Predictions about the distant future depend on current models and available evidence. New discoveries may alter these conclusions significantly. The history of cosmology repeatedly shows that the universe often surprises us. A century ago, humanity did not even know other galaxies existed beyond the Milky Way. Today, scientists attempt to model the fate of the entire observable universe. And as researchers continue studying dark energy, they also search for clues hidden much farther back in time, near the earliest moments after the universe itself began. When people hear about the Big Bang, they often imagine an explosion happening somewhere in space. But modern cosmology describes something more unusual. The Big Bang was not an explosion inside pre-existing space. It was the rapid expansion of space-time itself. Every region of the observable universe emerged from an earlier state that was far hotter, denser, and more compressed than today. The evidence for this picture is remarkably strong. Galaxies are moving apart through cosmic expansion. The universe contains a faint background glow called the cosmic microwave background. Light elements such as hydrogen and helium appear in proportions predicted by early universe nuclear physics. Together, these observations support the idea that the universe evolved from an extremely hot early state, roughly 13.8 billion years ago. But when cosmologists study the earliest moments of the universe carefully, difficult questions emerge. Why does the universe appear so geometrically flat? Why is the cosmic microwave background so uniform across enormous distances? How did tiny early fluctuations eventually grow into galaxies and clusters? To address these puzzles, physicists developed the theory of cosmic inflation. Inflation proposes that the universe underwent an extremely rapid burst of expansion during its earliest fraction of a second. Not ordinary expansion, exponential expansion. During inflation, space-time itself expanded enormously in a tiny interval of time. Regions once microscopically close became stretched across vast cosmic distances. The idea may sound strange at first, but inflation helps explain several important observations simultaneously. One major puzzle involves the uniformity of the cosmic microwave background. This faint radiation fills the universe almost evenly in all directions. Temperatures differ only by tiny fractions of a degree. Without inflation, distant regions of the observable universe would never have had enough time to exchange information or energy before emitting this radiation. They appear too far apart to have coordinated their temperatures naturally. Inflation resolves this by proposing that those regions were once much closer together before rapid expansion stretched them apart. Early thermal equilibrium became imprinted across enormous distances. Inflation also helps explain why spacetime appears nearly flat geometrically. Rapid expansion smooths curvature, much like inflating a balloon, makes small local regions appear flatter. The larger the balloon becomes, the flatter a tiny patch appears to an observer standing on it. Another remarkable aspect of inflation involves quantum fluctuations. During inflation, tiny quantum fluctuations in the early universe became stretched to cosmic scales. These slight density variations later served as seeds for galaxies and large-scale structure formation. In other words, the distribution of galaxies across the modern universe may ultimately trace back to microscopic quantum fluctuations during the earliest moments of cosmic history. This connection between quantum physics and cosmology is one of the most fascinating features of modern science. Tiny fluctuations at subatomic scales eventually influenced structures spanning billions of light-years. Inflation itself is usually modeled using another scalar field, similar in some ways to the quintessence ideas discussed earlier. During the inflationary era, the field possessed enormous potential energy. This energy drove rapid, accelerated expansion. Eventually, inflation ended. The field decayed into particles and radiation, filling the universe with hot plasma. From there, ordinary cosmic evolution continued. Expansion slowed compared to the inflationary burst. Matter formed. Atoms emerged. Stars and galaxies eventually appeared. Interestingly, inflation and dark energy share a conceptual similarity. Both involve accelerated expansion driven by energy associated with fields or spacetime itself. But they operate at vastly different strengths and eras. Inflation occurred extremely early and expanded the universe tremendously fast. Dark energy appears weak by comparison. Its effects dominate only over billions of years in the later universe. Some physicists, therefore, wonder whether deeper connections exist between inflation and dark energy. Could both phenomena emerge from related physics? Could scalar fields play recurring roles throughout cosmic history? These questions remain open. Modern cosmology still lacks a complete understanding of the universe's earliest moments. One reason is that conditions near the beginning of the universe involve energies far beyond those accessible in present-day particle accelerators. The early universe functioned almost like a natural high-energy physics laboratory. Physicists, therefore, rely heavily on indirect evidence preserved in cosmic structure and radiation. Tiny temperature variations in the cosmic microwave background contain valuable information about the early universe. Satellite missions such as COBE, WMAP, and Planck map these fluctuations with extraordinary precision. The patterns observed align remarkably well with inflationary predictions. Small, nearly scale-invariant fluctuations. Acoustic peaks shaped by plasma oscillations in the early universe. A cosmos that evolved from simple early conditions into complex large-scale structure. Yet, inflation is not fully proven. Many versions of inflationary theory exist. Different models predict slightly different behaviors. Cosmologists continue searching for observational signatures that could distinguish among them. One important target involves primordial gravitational waves. Some inflationary models predict ripples in spacetime generated during the earliest moments of expansion. These waves could leave faint polarization patterns in the cosmic microwave background. Detecting such signatures would provide powerful evidence about the physics of the infant universe. So far, no definitive detection has been confirmed. The study of the early universe also raises profound questions about beginnings themselves. Did time truly begin at the Big Bang? Or does the Big Bang represent a transition from some earlier state? Current physics cannot answer these questions completely. General relativity predicts singularities under certain conditions. Regions where densities become extremely large and current equations break down. Most physicists suspect a complete theory of quantum gravity will eventually modify this picture. Quantum gravity remains one of the great unfinished goals of theoretical physics. Scientists seek a framework unifying general relativity with quantum mechanics consistently. String theory and loop quantum gravity represent two major approaches among several possibilities. None has yet been experimentally confirmed. Dark energy may ultimately connect to these deeper questions. Understanding vacuum energy, space-time structure, and cosmic expansion likely requires insights from quantum gravity itself. In this sense, dark energy is not an isolated mystery. It sits within a much larger effort to understand the fundamental structure of reality. There is something remarkable about how much humans have already learned. Tiny creatures on a small planet orbiting an ordinary star have reconstructed much of cosmic history through mathematics, observation, and patient reasoning. At the same time, enormous mysteries remain. Most of the universe appears invisible. The earliest moments remain uncertain. Dark energy continues accelerating cosmic expansion for reasons not fully understood. Modern cosmology, therefore, exists in an unusual balance between precision and mystery. The equations work extraordinarily well. Yet some of the deepest underlying explanations remain incomplete. And perhaps that combination is part of what makes the universe so compelling to study. The more carefully humanity observes the cosmos, the more the universe reveals both structure and unanswered questions waiting far beyond the edge of current understanding. Modern cosmology is often described as a precision science. Telescopes map billions of galaxies. Satellites measure faint radiation left from the early universe. Computers simulate cosmic evolution across immense scales. And yet, despite all this progress, dark energy remains one of the greatest unsolved mysteries in physics. Scientists know the universe is expanding. They know the expansion is accelerating. Multiple independent observations confirm this consistently. But the deeper cause behind that acceleration is still uncertain. Because of this, researchers around the world continue building new instruments and experiments designed to study dark energy more precisely than ever before. One major strategy involves mapping the large-scale structure of the universe. Galaxies are not distributed randomly through space. They form enormous cosmic webs, filaments stretching across hundreds of millions of light-years, vast clusters connected through gravity, giant voids separating regions of matter. The shape and growth of this cosmic web depend partly on how expansion changes over time. Dark energy influences how quickly structures form and separate. By studying galaxy distributions carefully, astronomers can test different models of cosmic expansion. Tiny statistical patterns become clues about the behavior of dark energy itself. One important feature cosmologists study is called baryon acoustic oscillations. In the early universe, matter and radiation formed a hot, dense plasma. Pressure waves moved through this plasma, somewhat like sound waves traveling through air. When the universe cooled enough for atoms to form, These oscillations left subtle imprints in the distribution of matter. Today, astronomers can still detect these patterns statistically across enormous galaxy surveys. They function almost like cosmic rulers, helping scientists measure expansion history across billions of years. Another major approach involves weak gravitational lensing. According to general relativity, massive objects bend spacetime and deflect light passing nearby. Large concentrations of matter therefore subtly distort the appearance of distant galaxies. These distortions are usually extremely small. Individual galaxies appear only slightly stretched or skewed. But by analyzing millions of galaxies statistically, astronomers can map how matter is distributed throughout the universe. Because dark energy affects cosmic expansion and structure growth, lensing measurements provide another important test of cosmological models. Supernova observations also continue playing a central role. Astronomers now discover and measure far larger numbers of type Ia supernovae than were available during the original acceleration discovery in the 1990s. Improved data reduces uncertainties gradually. Modern cosmology depends heavily on combining many independent measurements together. No single observation alone reveals the entire picture. Instead, multiple lines of evidence reinforce or challenge cosmological models collectively. Several major observatories are now dedicated partly to this effort. The Euclid Space Telescope, launched by the European Space Agency, aims to map billions of galaxies across a large fraction of the sky. Its mission includes studying dark energy through galaxy clustering and weak lensing measurements. The Vera C. Rubin Observatory in Chile is another major project. Equipped with an enormous digital camera, it will repeatedly scan the night sky over many years. This survey will generate vast datasets involving galaxies, supernovae, asteroids, and transient cosmic events. The Nancy Grace Roman Space Telescope, planned by NASA, will also investigate dark energy through high-precision cosmological observations. Together, these projects represent one of the largest coordinated scientific efforts ever devoted to understanding cosmic expansion. Cosmology increasingly depends on enormous amounts of data. Advanced statistical methods and machine learning tools now assist researchers in analyzing complex observations. Tiny deviations hidden within massive datasets may reveal important clues. Yet the challenge is not only observational. Theoretical physics also continues searching for deeper explanations. Some researchers study quantum vacuum energy. Others explore modified gravity, scalar fields, extra dimensions, new particle physics frameworks. One particularly important issue in recent years is something called the Hubble tension. The Hubble constant measures the present expansion rate of the universe. Different methods for estimating this value produce slightly different results. Measurements based on the early universe sometimes disagree with measurements based on nearby supernova observations. The discrepancy is not enormous, but it persists carefully across multiple studies. Scientists continue debating whether this tension reflects unknown measurement systematics or hints of new physics beyond the standard cosmological model. Some proposed explanations involve evolving dark energy. Others involve neutrino physics, early universe modifications, or changes to cosmological assumptions. No consensus has yet emerged. This illustrates an important feature of science. Even highly successful models are continually tested against new evidence. Small discrepancies sometimes disappear with improved measurements. Sometimes they lead to major discoveries. The history of physics contains many examples of this process. Tiny anomalies in Mercury's orbit contributed to general relativity. Unexpected atomic behavior led to quantum mechanics. Strange galaxy rotations revealed evidence for dark matter. Dark energy itself emerged because observations refused to fit earlier expectations about a slowing universe. There is therefore a quiet balance within modern cosmology. Confidence and uncertainty coexist. Scientists possess extraordinarily detailed measurements of the universe. Yet fundamental questions remain unresolved. This uncertainty is not weakness. It is part of how science advances. Questions motivate new observations. New observations refine theories. The process continues gradually across generations of researchers. Dark energy research also demonstrates how collaborative modern science has become. Thousands of scientists contribute to telescope design, detector engineering, data analysis, theoretical modeling, and computational simulations. Cosmology now spans continents and decades of coordinated work. The scale of these efforts mirrors the scale of the questions themselves. Humanity is attempting to understand the long-term evolution of the entire observable universe. And remarkably, much of this understanding emerges from faint traces of light traveling billions of years through space. Tiny distortions in galaxy shapes, subtle shifts in spectra, slight differences in microwave radiation. The cosmos leaves clues everywhere. Science advances by learning how to read them carefully. Even if dark energy is eventually explained fully, the answer will likely open new questions beyond it. This has happened repeatedly throughout scientific history. Each deeper layer of understanding reveals additional mysteries underneath. In many ways, cosmology is still young. The expansion of the universe was discovered less than a century ago. Dark energy was identified only in the late 1990s. Future generations may look back on the current era as an early stage in humanity's understanding of cosmic structure. For now, the universe continues expanding quietly in every direction. Galaxies drift apart across immense darkness. Light travels for billions of years before reaching observatories on Earth. And somewhere within that vast expansion, the mystery of dark energy continues waiting to be understood more deeply. Dark energy is often described as one of the greatest mysteries in science. But mysteries in physics are different from mysteries in fiction. They are not hidden secrets waiting dramatically behind a door. They are careful gaps between observation and explanation. Scientists observe something real. The universe is expanding faster over time. Multiple independent measurements support this conclusion strongly. Yet the deeper reason remains uncertain. In many ways, dark energy represents the edge of current human understanding. a place where modern theories work remarkably well in some respects, yet remain incomplete in others. This situation is not unusual in the history of science. Humans often understand patterns before fully understanding causes. Ancient astronomers tracked planetary motion long before gravity was understood mathematically. Electricity was studied before electrons were discovered. Spectral lines were measured before quantum mechanics explained atoms. Observation frequently comes first. Deeper explanation follows gradually. Dark energy may represent another stage in that long process. Humanity can measure cosmic acceleration with increasing precision. Yet the ultimate origin of that acceleration remains open to investigation. There is something remarkable about the scale of this question. Human beings evolved to navigate forests, rivers, weather, and social groups. The human brain did not evolve to intuitively understand expanding spacetime, quantum fluctuations, or billion-light-year structures. And yet, through mathematics and observation, humans gradually learned to study realities far beyond ordinary sensory experience. Telescopes extended vision. Equations extended reasoning. Instruments detected signals invisible to human senses. Cosmology therefore reveals something not only about the universe, but about human curiosity itself. The night sky appears peaceful from Earth. Stars move slowly across darkness. Galaxies look still and silent. Yet beneath that calm appearance, the cosmos evolves continuously across unimaginable scales. Space expands. Galaxies drift apart. Gravity shapes matter into structure. Quantum processes fluctuate invisibly throughout vacuum fields. Dark energy reminds scientists that even emptiness may possess properties not fully understood. The vacuum itself may participate in cosmic evolution. This challenges older intuitions about reality. For much of history, empty space was imagined as passive nothingness. Modern physics instead suggests that space may contain geometry, energy, quantum structure, and dynamic behavior. Even the concept of nothing becomes surprisingly complex under careful scientific examination. There is also a deeper philosophical quietness in cosmology. The universe does not organize itself around human scale or comfort. Cosmic evolution unfolds across billions of years, regardless of human concerns. Stars formed long before life appeared on Earth. Galaxies will continue evolving long after current civilizations disappear. And yet, for a brief moment within this enormous timeline, conscious beings became capable of reflecting on the universe itself. That fact alone is extraordinary. Matter organized into biology. Biology evolved into intelligence. Intelligence developed mathematics and scientific reasoning. Eventually, tiny creatures living on one planet began measuring the expansion of spacetime itself. The process was gradual. Thousands of years of observation, generations of accumulated knowledge, improved instruments, better mathematics. Science advances slowly compared to individual human lives. Dark energy research continues in that same tradition today. Many researchers spend decades refining measurements by small percentages. Tiny statistical improvements matter because cosmology depends on extraordinary precision. From the outside, these efforts may appear abstract, but collectively, they contribute to humanity's broader attempt to understand existence at the largest scales accessible to observation. There is also an important lesson in how scientists approach uncertainty. In everyday life, uncertainty often feels uncomfortable. People naturally prefer clear answers and stable conclusions. Science works differently. Uncertainty is measured carefully rather than avoided. Good theories are tested repeatedly. Models remain open to revision if evidence changes. This willingness to update understanding is one reason science progresses over time. Dark energy itself was accepted because observations demanded it, even though the conclusion initially surprised many cosmologists. In that sense, dark energy reflects intellectual humility as much as discovery. The universe does not always match human expectations. Careful observation matters more than intuition. There is also beauty in the interconnectedness revealed by modern cosmology. Tiny quantum fluctuations in the early universe influenced galaxy formation billions of years later. Gravity shaped stars where heavy elements formed. Those elements later became planets and living organisms. Humans themselves are products of cosmic history. Carbon from ancient stars, oxygen from stellar fusion, atoms recycled through generations of supernovae. Studying the universe, therefore, also means studying the larger processes that made life possible. Dark energy may seem distant from everyday experience. Its effects are noticeable mainly across enormous scales. Human bodies do not feel cosmic expansion directly. Galaxies themselves remain gravitationally bound internally. Yet dark energy still influences the long-term structure and destiny of the observable universe. Over immense timescales, it shapes how galaxies separate and how the cosmos evolves. One day, future civilizations may understand dark energy far more deeply than current science does. Concepts that appear mysterious today may eventually become standard parts of physics education. This has happened repeatedly throughout history. Electricity once seemed mysterious. So did magnetism, radioactivity, relativity, quantum mechanics. Over time, unfamiliar ideas became integrated into broader scientific understanding. Perhaps dark energy will follow a similar path. Or perhaps it will lead to an even deeper transformation in physics. Some scientists suspect that solving dark energy may require entirely new frameworks for understanding spacetime and quantum reality. Others believe the answer may emerge gradually from improved observations within existing theory. At present, no one knows with certainty. And that uncertainty is part of what keeps cosmology active and alive as a field of research. The universe still contains unanswered questions large enough to occupy generations of scientists. Tonight, as Earth rotates quietly beneath the stars, galaxies continue moving apart across expanding space. Light from distant regions of the universe continues traveling toward Earth through immense darkness. And across observatories around the world, scientists continue searching for clues hidden within that ancient light. Because somewhere within the structure of space-time itself, the answer to dark energy may already be written into the universe, waiting patiently to be understood. For thousands of years, human beings looked upward and wondered what the universe truly was. Ancient observers traced the motion of stars across the night sky. Early civilizations built calendars from celestial cycles. Philosophers debated whether the cosmos was eternal or changing. The sky inspired both curiosity and humility long before modern science existed. Today, humanity understands far more about the universe than earlier generations could have imagined. Earth is one planet orbiting an ordinary star within the Milky Way galaxy. The Milky Way contains hundreds of billions of stars. Beyond it exist hundreds of billions of other galaxies spread across expanding spacetime. Modern cosmology revealed that the universe evolves dynamically. It had a hot early beginning. Galaxies formed gradually through gravity. Stars created heavier elements through nuclear fusion. Black holes emerged. Planets formed. Life appeared on at least one world. And yet, despite all this knowledge, much of the cosmos remains mysterious. Dark matter appears invisible, yet shapes galaxies gravitationally. Dark energy drives accelerated expansion across enormous scales. Quantum gravity remains incomplete. The earliest moments of cosmic history are still uncertain. In some ways, modern science has revealed not only answers, but the vastness of what remains unknown. Dark energy stands near the center of that mystery. It appears to dominate the large-scale behavior of the universe. And yet its true nature remains unresolved. Is dark energy simply vacuum energy built into space-time itself? Is it a dynamic field evolving across cosmic history? Does it point toward modifications of gravity? Or does it hint at entirely new physics still undiscovered? At present, no final answer exists. The universe continues keeping some of its deepest structures partially hidden from understanding. But there is also something quietly beautiful about that uncertainty. Science is not only a collection of facts. It is also a process of exploration, a gradual refinement of humanity's picture of reality. Each generation inherits questions from the one before it. Some mysteries are solved. Others deepen into even larger questions. Cosmology especially encourages this long perspective. Human lives are brief compared to cosmic timescales. Civilizations rise and fall within tiny fractions of the universe's history. Even entire species are temporary within cosmic evolution. And yet, within that brief window, conscious beings became capable of studying galaxies billions of light years away, capable of reconstructing the history of cosmic expansion, capable of detecting faint microwave radiation left from the early universe. This achievement emerged slowly through observation, mathematics, engineering, and collective human effort across centuries. Telescopes grew larger. Detectors became more precise. Equations became more refined. Scientific knowledge accumulated gradually across generations. The story of dark energy is therefore also part of the story of human curiosity. A species attempting to understand a universe vastly larger than itself. There is a quiet contrast here. Human experience feels immediate and local. Days pass through ordinary routines. Weather changes. Cities move through time. Yet beyond everyday life, the cosmos expands continuously in every direction. Galaxies drift farther apart through spacetime. Ancient starlight travels across billions of years before reaching Earth. Black holes shape regions of space invisibly. Quantum fluctuations ripple beneath physical reality itself. Much of this unfolds silently, beyond direct human perception. Science provides tools that extend awareness beyond ordinary senses. In this sense, cosmology changes perspective. It places humanity within a much larger physical context, not at the center of the universe, not separate from cosmic history, but part of an evolving cosmos governed by consistent physical laws. Even the atoms within human bodies originated through cosmic processes. Hydrogen formed near the beginning of the universe. Carbon and oxygen formed inside stars. Heavy elements emerged through stellar explosions and neutron-star collisions. The universe became complex enough for life because earlier generations of stars transformed simpler matter into richer chemistry. Dark energy now influences the future evolution of that same universe. Across immense scales, expansion continues accelerating. Distant galaxies recede farther into darkness. Over unimaginable timescales, cosmic structure itself will gradually change. Yet from the human perspective, the night sky still appears calm and familiar. Stars continue rising above Earth, much as they did for ancient observers thousands of years ago. There is something grounding about that continuity. Humans remain connected to the same cosmos, studied by every earlier generation. The questions evolved. The tools improved. But the basic curiosity remained remarkably constant. What is the universe? How did it begin? Why does it behave this way? What will happen in the far future? Dark energy enters that long chain of questions as one of the newest and most profound scientific puzzles. Its discovery reshaped modern cosmology unexpectedly. A universe once assumed to slow down turned out, instead, to accelerate outward. That discovery reminds scientists to remain open to surprise. Nature does not always align with intuition or expectation. Careful observation remains essential. Future discoveries may eventually explain dark energy fully, or they may reveal even deeper mysteries underneath it. Either outcome would continue the process of scientific exploration. For now, humanity exists in an unusual moment, advanced enough to measure the expansion of the universe, yet still early in understanding its deepest foundations. Perhaps centuries from now, future scientists will look back on the present era as the beginning of a much larger transformation in cosmology. Or perhaps the answers already exist quietly within equations and observations waiting to be recognized more clearly. Tonight, beyond Earth's atmosphere, the observable universe continues stretching outward through immense darkness. Galaxies drift across expanding spacetime. Ancient photons continue their journeys through the cosmos. And within that vast, evolving universe, human beings continue searching for understanding. Slowly, carefully, one observation at a time.